Okay, boys and girls, welcome to section 4.6. It's on isosceles and equilateral triangles. I am not here today, or when this video is made the next day, because my wife and I had our baby this week. We had it the Tuesday before Thanksgiving. So before we do all the fun stuff, there is a picture. You can ooh and ah for a minute. Say hello to Zane. Hello, Zane. And now we'll start. Okay, so section 4.6, isosceles and equilateral triangles. We're going to start with the isosceles triangle theorem. It is called the isosceles triangle theorem, so I made a fancy capital T and everything. Alright, and what it says is if two sides of a triangle are congruent, then the angles opposite those sides are congruent. So what we're saying is if this side is the same as this side, then the angle opposite those congruent sides are congruent. So if AB is congruent to AC, that would mean then angle B is congruent to angle C. So this is really good SAT stuff that you guys will want to remember. That when you have an isosceles triangle, the angles opposite the congruent sides are congruent. Now, sometimes I forget to tell people, I don't mean to do it, but I forget to tell you about the parts of an isosceles triangle. So let's go over that real fast in case it doesn't come up again, which it probably will, but we'll do it anyway. Alright, so I designated these two to be the same. These are called legs. The congruent sides are called legs. Now, the intersection of the legs is the vertex angle. So when you hear something reference the vertex angle of an isosceles triangle, it's talking about the angle between the two congruent sides. And then what we know is that the base is the one that's not the legs, and then you have base angles, and so we say that the base angles are congruent. And those are the parts that you'll hear referenced when you're talking about isosceles triangles. The legs are the congruent ones. The vertex angle is the one formed by the two congruent legs. The side that's not a leg is called the base, and it doesn't have to be on the bottom, it's just the one that's not congruent to the other two. And then the base angles. Now, when you're using this as justification and proof, you can call it the isosceles triangle theorem. But in a second, we're going to see the converse of it. So then I start to forget which was the original and which was the converse. And so I like to actually write it in symbols, and you're welcome to do the same. When I'm using isosceles triangle theorem as justification and proof, I write if the sides are congruent, then the angles are congruent. And then that way I don't have to remember about or worry about which one was first. Was it the isosceles triangle theorem or the converse? Alright. Now, we can prove that if we want to, and it shouldn't be too hard to do, knowing all the stuff that we know. So let's do that. This is another one. I'm going to mark what we're given. That this congruent to PQ is the same as RQ. I want to show that angle P and angle R are the same. And this is going to be another one, boys and girls, where we will draw an auxiliary line as our first thing. So I'm going to draw this auxiliary line. But I don't want to draw just an arbitrary one. I want to draw a specific one, PQRS. That's the next one after that. There we go. So I want to draw QS. I want to draw it in a certain way. and I actually have lots of choices, I'm going to draw QS angle bisector of angle PQR. Now I said there's lots of choices. Other choices include you could make it perpendicular if you wanted to, would be a way to do it. You could, if you wanted to, make it the bisector of PR, would be another way to do it. I chose this way because that's the first thing I thought of. Oh, and I hope you're enjoying the Christmas music because it's that time of year. So, if I make this my statements, and over here my reasons, alright, this would be through any 2 points, one line. And now we've done the hard part. Let's look at it and talk about it before we write it out. But when I drew this, I made 2 of these triangles. What did we spend a good time of chapter 3 doing? Or chapter 4? I'm sorry, chapter 4, we proved triangles congruent. And that's what we're going to do here, is we're going to show these 2 triangles are the same. That means all their parts are the same, which means those 2 angles would have to be the same. And so the method I've chosen is I know QS is going to be congruent to itself, and then I chose to bisect that angle, which is going to give me side, angle, side. If you bisect PR instead, then you got side, side, side. Or if you choose to make it perpendicular, you have hypotenuse leg. But you'll have to hold on to hypotenuse leg because we haven't done it in class yet. So your 2 choices are really bisect the angle or bisect the segment. Alright, so I bisected the angle. So that means that angle PQS, rats, is congruent to angle RQS, because that's what angle bisectors do. They form congruent angles. I know that PQ is congruent to RQ. They were nice enough to tell me that. And of course, QS is congruent to itself. It has to be the exact same size as itself. So as we always want to do, I have shown that I've got 1, 2, 3 congruent parts. If I got 3 congruent parts and they're the right ones, then I have congruent triangles. So triangle PQS is congruent to triangle RQS by the side angle, side postulate. And if the triangles are congruent, then all 6 of their parts are congruent. So angle P is congruent to angle R because the corresponding parts, of rats. There, stay. Yeah, don't even know what to say. Let's try that again. Because the corresponding parts of congruent triangles are congruent. Alright, CPCTC, corresponding parts, congruent triangles are congruent. Alright, that's a proof I like to have show up occasionally on stuff. So the converse of that is also true. That if 2 angles of a triangle are congruent, then the sides opposite those angles are congruent. So this time we're taking it a different way. We're saying that if angle A is congruent to angle E, then the sides opposite those angles are congruent. So this is another one that I use the symbols for, so I don't have to remember which was the original and which one's the converse. I just write it this: if the angles are congruent, then the sides opposite those angles are congruent. And let's take a quick peek ahead. Okay, good. I'm not proving this one because maybe it's going to be a homework problem sometime. But if I had to prove this one, I would be given that and that. So So I'm going to follow the same strategy. I just don't think I have quite as many options. I'm going to draw myself an auxiliary line. You can do the sound effects too. And I know it's congruent to itself. So I can do an angle bisector here and here. And I've got angle, angle, side. If I did the segment bisector, let's get the magic pen. If I did the segment bisector for this one, I'm going to be in trouble because it's going to give me angle, side, side. And angle, side, side's bad. Alright, so you either want to do what I've done here and bisect the angle, or you want to make it perpendicular so that you get angle, angle, side that way. Right? But that's the strategy for that. Either bisect the angle or make it perpendicular. And then the proof will be the same. Triangles congruent, then all their parts are congruent because the corresponding parts of congruent triangles are congruent. Alright, let's go on. Example proof. I know that the distance from A to B is the same as the distance from C to B. So let's mark this stuff up because that's a lot. So A to B is the same as C to B. And that's the same as B to D. So I want to prove that angle ACB, that's that angle, is the same as angle BCD, that's that angle. Okay, shouldn't be a big deal. We have two isosceles triangles. So that means I have two sets of congruent angles. And so let's just do sort of a paragraph proof. Since AB is the same as BC, that's a B, sorry. Alright, since AB is the same as BC, angle BAC is the same as angle BCA. And since BC is the same as BD, that means that angle DBC is the same as angle BCD. So we're trying to show that this guy and this guy are the same. Alright, but we already know that the two I drew arrows to are the same. Uh-oh. Let's see, I have DBC. There's no DBC. Hold on. BCD goes with BDC. That's our problem, or my problem. You're probably doing fine. BDC. Alright, so this one's angle A, and this one's angle D. I know these two are the same. That means that these two are the same. So you can just go to substitution after you explain all that stuff to show that they're the same. Alright, let's recap that one again because I butchered it a little bit. But it's not that bad, and I'll read it again. Okay. I have two isosceles triangles. So this angle is the same as this angle. This angle is the same as this angle. Then I'm given that these two are the same. So if these two are the same, then those two must be the same. Alright, let's do the next one. A number type problem. This should be fun. It says that DE is the same as CD, and BC is the same as AC, and the measure of angle CDE is 120. What is the measure of BAC? That's this guy. Alright, so we know that triangles always add up to 180. So if this guy is taking up 120, that means that the other two angles get 60 to share. But because it's isosceles, that means that these two angles are congruent. And so they get to share that evenly, so each of these are 30. Then we have our good friend vertical angles being congruent. So if this one's 30, this one's 30. Whoa. Triangles add up to 180, and that vertex angle is taking up 30, which means angle B and angle A get to share 150 degrees. But they do it equally because that's also an isosceles triangle. So angle A would be 75 degrees. Alright, a couple of corollaries for this chapter. Go with the isosceles triangle theorem. It says a triangle is equilateral if and only if it's equiangular. So sure, if the angles are the same, then the sides opposite those angles are the same. And if a triangle has three sets of congruent, all three sides are congruent, then we call it equilateral. Likewise, the only way I can get equiangular is if all the sides are the same. So the angles opposite those would be the same. And then 180 divided by 3 is 60. So since all the angles are the same, and they always add up to 180, 180 over 3 is 60. So each one would be 60. So you could prove those easily enough if you were ever asked to do so. Alright. Now that is everything for this section. Now because I'm not here, and I'm making this swell video, I have actually taken the unusual step of assigning the odd problems. Alright? That means you can check in the back of the book. That's because tomorrow we're going to review for our test. We have a test on Thursday. I speeded the process up a little bit so we can get done everything that we need to get done this semester. So that test Thursday will cover sections 4.1 through 4.6. Now, 4.7 I usually skip unless we're doing great on time, which we're not because it's after Thanksgiving, because you'll cover that in Algebra 2. I actually saw Dr. Kaler's Algebra 2 exam this morning, and it has that on there. So you'll cover that in Algebra 2. Now 4.8 we will come back to at some point because I really like it. And to me it's one of the things that separate honors from regular, from on level, is the coordinate proofs. It's proofs with algebra. You're going to love it. Alright, so I gave you odd problems. Check them in the back of the book. Bring your questions tomorrow. We'll review for the test, and the test is on Thursday. Alright? Also, if you feel like you need extra practice, you can do even ones, and you can check them in my book if you want. Alright, thanks for watching. That was fun.